Now, when resonance happens, we have to understand when resonance happens. What are the cases resonance happen? When resonance does happens, we can say like this. So here, number one, if it is lone pair, sigma, pi, etc., that is lone pair, sigma, pi, kind of rhythm. Number two can be pi, sigma, pi, can be again alternately pi, sigma, pi. Number three, we can say that is lone pair, or we can say that pi, sigma, empty orbital. So in that case also this can happen, that is pi, sigma, empty orbital, pi, sigma, empty orbital, like this it can happen. Number four, once again we can write odd electron, sigma, pi kind of situation, that is odd electron sigma pi kind of thing. Number five, that is lone pair and empty orbital. So you have to understand where and how resonance happens in cases where the resonance happen. Now to explain with this, I will take one by one the cases. Let's say I am taking lone pair sigma pi situation. Let's say I am talking about NH2 CH double bond CH2. So over here you can see that the case 1, I am taking case 1, it is like this. So here the lone pair is over here. Now this lone pair can come over here and pi bond can go over here. So you can get NH2 plus double bond CH, CH2 minus. Now my dear students, how it happens, how this kind of situation happens, just look at nitrogen orbital picture. If you see this, basically NH2 is in the plane and the lone pair is in 2pz in the first structure, and then the CH basically like this, CH2 over here it is again plus, it is your plus 1 electron, so over 1 electron, so they are making the pi bond before, and this is also plus, let's say minus. It is, let's say, structure 1, so it is structure 1 dash. Now what happens is that this, since this orbital is parallel to this, so this can again make their contribution like this. They can make overlap, and these two electron can go over here. So 2 dash structure like this. In it is your like this on the plane, it is like this. Here it is this CH2 CH2 again over here the 2 electron will be coming over here. This is the plus, this 1 electron over here, this 1 electron over here, and it becomes plus like this. So therefore primarily you must know that when suppose it is 2 dash, so that means what, these two are basically canonical structure. When you write resonating structures or canonical structure, you must put this kind of arrow between these two structure. So these are basically the resonating structure of the molecule, and this is basically vinylamine. So therefore we can say that basically lone pair goes over here from nitrogen into carbon end. So this way, if the electron pair moves in the molecule or a single electron moves in the molecule gets extra stability. Since it has got two structure, we can call these are resonating structures. So therefore to draw the resonating structure, you must understand beforehand that the lone pair is in 2pz, and this 2pz making pi bond. So therefore it is making the pi bond next stage. So it will be like this, and this carbon is having minus charge and this nitrogen having plus charge. So this way we can see the resonating structure with 1 per sigma pi. So that means it can be extended like this: NH2, let's say CH double bond CH, CH double bond CH2, like this. This way we can go for further resonating structure like this, and then this will come, this will go like this. You can get three total resonating structure. Here we are getting 2 resonating structure, and this kind of situation pi sigma pi, this is called pi, this pi sigma pi. This kind of situation is also called conjugation. We use the term called conjugation. So therefore pi sigma pi sigma, this kind of situation is called conjugation. So here lone pair goes inside the conjugation, so making extra stability of the molecule, and effect of this is that over here you can check that here CN single bond, but in the second structure it is double bond. That means what, CN bond, basically CN bond is shorter. CN bond is shorter than the CN normal sigma bond, CN sigma bond, because it looks that it is sigma bond but it's not sigma bond, it has got double bond character at this point. So obviously this is basically the situation where we find that CN bond shortens from the normal CN bond, sigma bond. Same thing can also happen. Suppose if I say chlorobenzene, over here, or you can say vinyl chloride, CHCl, like this situations, the resonance takes place. So like this, and this will come over here, this will go, this will come over, this will go, and this will come over, this will go. So this way resonating structure can take place. If I talk about vinyl chloride, look over here, just like this, it can get another resonating structure. There is CH2 minus, it is your CH double bond Cl plus. Try to understand, my dear students, that CCl bond is getting double bond character. So if CCl bond gets double bond character in chlorobenzene or vinyl chloride, obviously the CCl bond becomes stronger, not like single CCl bond. So next we can say number 2, case 2, that is your basically pi sigma pi. It's very simple. Let's say CH2 double bond CH double bond CH2, just like this. It's a butadiene. Over here, this pi one goes over here, this pi one goes over here. So we can draw the resonating structure CH double bond CH2. It is your minus, it is your plus, and also you can see that this double bond can go over like this. So we can say that it is CH2 minus, it is CH double bond CH, it is a CH2 plus, like this. So 1 and 2 and 3. This kind of 3 resonating structures are possible for buta 1,3-diene, buta 1,3 diene. Now I will tell you the beauty of this particular molecule, buta 1,3-butadiene. So if you see the MO diagram, how it stabilizes, extra stability happens with the molecule, I will tell you. For example, let's say I am taking butadiene, CH2 double bond CH double bond CH2. How it forms? There you can see that 1 pi bond, that is 2 pi electrons, and this 2 pi electron, that means total 4 pi basically coming into the making the pi bonds on all 4, C1, C2, C3, C4. This kind of situation is happening. These are all, let's say, 2pz orbitals of carbon. Now look over here, this can be a situation where you can have all plus like this, all plus like this, minus, it is your plus, it is your minus, it is your plus, it is your minus. This kind of situation can happen. So this is giving the bonding MO, that is pi 1, let's say it is a pi 1. It can happen like this, that it is becoming like this, that it is like this, it is like this, it is like this, it is minus, minus, plus, plus. So there is a pi bond MO, plus, plus, minus, minus. There can be pi bond MO, this it is pi 2. These are all bonding MOs. Now you can go for anti-bonding MOs, like it can be like this plus, it is like this minus, it is your minus plus, and it is your, let's say it is your plus minus. So therefore there will be like this situation, and the fourth one will be basically the structure will be like this, that is all basically are the asymmetric condition. So obviously we can say like this, that it is like this. So plus minus minus plus, plus minus minus plus. So obviously this is the most unstable anti-bonding MO. This is pi star, let's say pi 4, let's say pi 4 is anti-bonding, it is pi 3, let's say over here, and it is like nothing but pi 2 and is pi 1. Obviously it is the very central line, the mean energy line. So all p orbitals are making the pi 1. So therefore pi 1, pi 2, pi 3, pi 4, this kind of situation will happen. This is a most unsymmetric situation, and since we know 4 pi electrons are there, so therefore the 2 pi electron will be taking part over here, and 2 pi bonds are like this, and the anti-bonding MOs are basically the unfilled, and this is called LUMO, this is called LUMO, and this is called HOMO. That is, this situation arises for this case. So therefore these are basically the situation of the buta 1,3-diene. If I talk about the MO diagram, this basically we are talking about the MO diagram. Now you can easily look at that how the molecule is basically existing, in butadiene, and how the resonance. That means what? The most stable conformation or structure, more stable structure is this, then this, then this, then this. So I have drawn the resonating structure on the basis of this. This is the most stable condition when all the orbitals have the same symmetry of the 4 carbon atoms.